Good evening. We will study today a topic which is quite important in this last unit of the course, and it is, as you will see later, one of the several theorems of the kind. So we're going to talk about the so-called fundamental theorem of line integrals. It has important applications in physics, and it will give us the opportunity to go even deeper into some of the connections between these mathematical tools and real-life applications. Those of you who have taken or will take physics courses, you may find some natural connections with the topics you studied already, and hopefully you can see them in a better light. But strictly mathematically speaking, the fundamental theorem of line integrals is another version of a fundamental theorem of calculus that you learn in Calculus 1, toward the end of Calculus 1. And so if you remember, just as a quick trip down the memory lane, the integral from a to b, the fundamental theorem of calculus, stated that if you want to integrate a function that has antiderivatives, the integral from a to b of that function is the antiderivative of that function evaluated at b and a, and take the difference, right? So everybody should know at this point, of course, this theorem, we use it repeatedly, right, whenever we integrate a function, where this big F again stands for the antiderivative of f of x dx. As a matter of fact, it's probably even more suggestive for our purposes to actually write this theorem like this. So if I have to integrate a derivative, big F prime of x dx, that's going to be big F evaluated at a and b. For our purposes, it's probably easier to, for our purposes today, it's probably easier to visualize it this way. So the definite integral of a derivative, it's the antiderivative evaluated at the endpoints. And let's expand this concept of the endpoints. This is essentially this function evaluated at the boundary of the domain. In this case, the boundary is just the endpoints of the segment AB, right, which constitutes the domain of the function. So hold that thought in your mind. And now let's move on to our topic of today. And I'm going to begin, I like to begin this topic before I even talk about what the fundamental theorem of line integral is all about, to actually go through yet one more example that I would like you to mirror with the example we did in the previous section toward the end of the class. So if you want, you can just pause the video and just go back to the previous lesson. And then there is one particular example when I show that if I evaluate a line integral over a vector field between for two different paths, two curves, starting and ending at the same point, typically we expect the integrals to be different, meaning that normally the line integral depends on both. So we can even write it down as a reminder. So normally line integrals depend on the path and the endpoints, right? So in other words, despite the fact that you may have multiple paths starting and ending at the same point, like you see here in this particular picture, normally the integral actually depends on the path taken from point A to point B. So let's actually go over another example of this kind, and let's see if we notice something different in particular. So here on the picture here, I sketched, hopefully it's big enough, I sketched two curves. One of them is a straight line, so let's call it C1, and as a vector function, this is minus 1 plus t, and then 1 plus t. And with the parameter domain between 0 and 1, meaning that the initial point, the starting point r of 0 is going to be minus 1 and 1, as you can see here. I write it as a position vector, but that, of course, the terminal point of it is the point minus 1, 1. And r of 1 is going to be 0, 2. And the other path, C2, let's say it has the components t minus 1 and t third plus 1. So let's call it also r of t minus 1, t third plus 1. And notice also that this one as well let me see here, the domain here for, yeah, the domain in this case, the parameter domain for the second curve will be 1 and 2. Let's see, hold on a second. No, still 0 and 1, the same thing. Yeah. 0 and 1. Doesn't have to be, but yeah, in this case it's just 0 and 1. So just like before, r of 0 is minus 1 and 1, and then r of 1 is 1 and 2. So I picked two curves that start and end at the same point. Let's compute the line integral for both of them for the following vector field. So this is going to be a line integral of a vector field. In particular, the components of the vector field are given by 3x minus y and minus x plus y squared. Okay, and then for the first integral, so the integral over the curve 1 of f dot dr, remember the typical notation for a line integral over a vector field, this will be the integral from 0 to 1. Let's evaluate the vector field at the first curve, so we're going to plug in minus 1 plus t for x and 1 plus t for y, or minus quantity minus 1 plus t plus 1 plus t quantity squared. And we're going to dot this with the r prime of t, which this is simple, is just 1, 1, right? R prime of t is 1, 1 dt. So we're going to come up with the dot product of this and then integrate. Sorry for the cutoff, the interruption here. Something happened and then just both the tablet app and the screen capture crashed. Happened before and makes me rethink the medium of exposition if I do it again with a different course. So let's continue. Just to summarize, I wrote this, put the sketch one more time here. Okay, so with the curves from minus 1, 1 to 0, 2. The vector field we're going to focus on, right? 3x minus 1, y minus x plus y squared. And let's evaluate the line integral over the first curve, which is the line segment from minus 1, 1 to 0, 2. So we plugged in the components of the curve into the vector field, set up the dot product with the derivative, dr, and then let's compute the dot product and then evaluate the integral. So we have to simplify a little bit the vector here. So we have minus 3 plus 3t minus 1 minus t, the first component. Then we have 1 minus t, and then let's expand that, plus t squared plus 2t plus 1 dot 1, 1. And let's just do the dot product at the same time, because that's easier in this case. So we have minus 4 plus 2t times 1. Minus 4 plus 2t quantity times 1, so it's not going to change. And then plus t squared plus t plus 2. Alright, so then when we finally compute this integral, we have t squared plus 3t minus 2. Integrate t third over 3 plus 3 t squared over 2 minus 2t between 0 and 1, which is 1/3 plus 3/2 minus 2. So if we simplify this a little bit, we have 2 over 6 plus 3 times 3, which is 9, minus 12 over 6, makes it 1 minus 1 over 6. Okay, so let's quickly do the other two, the other integral. So once again, let's focus on the main point we're trying to make here. Same vector field, but this time a different path between minus 1 and 1, between those 2 points. So I don't know if this is going to be feasible to do it on paper here. You may have to do it with the calculator, but let's just set it up and see what we get. I think it might be actually doable. It's not going to be too complicated. So for the second curve, so the integral from, so the integral over c2 of f dr is going to be the integral from 0 to 1, and now we're going to plug in the second curve c2. So look at the components of it into the vector field. So we have 3 times quantity t minus 1 minus quantity t third plus 1 comma minus x, so again minus quantity t minus 1 plus y squared, which is t third plus 1 squared. Okay. And then dot r prime of t, which is, in this case for the second curve, 1 3t squared. Alright, so let's simplify this a little bit. Bunch of power rules, so 3t minus 3 minus t third minus 1 minus t plus 1. We have to square that term. T to the 6, 2t third plus 1. And then dot with 1 and 3t squared. This might be a little bit tedious actually. Let me see if I can, I'll do it. Might as well do it and have this for practice. So the dot product between 3t minus t third minus 4, this is times 1, plus t sixth, 2t third minus t plus 2 multiplied by 3t squared dt. And then plus 3t to the power 8. We're going to have 6t to the power 5 minus 3t third plus 6t squared dt. And one more simplification, and then we're going to integrate. Let's write them in the order of decreasing order of the coefficients or the powers. We have minus 4t third followed by 6t squared, 3t minus 4. Anyway, you'll see my point that, I mean, I'm doing this so you can see, those of you actually who know this topic might anticipate actually what flows from here. But this example, which I strongly encourage you to do it just for practice, it'll come up with a surprise later on when we move on with the topic, when it comes to actually how we compute this in a much more efficient way. All right, so let's integrate. We have 3t to the 9 over 9 plus, this is t to the 6th minus t fourth followed by 3t third, 2t third, the antiderivative of that term, 3t squared over 2 minus 4t. And then finally we plug in 0 and 1, and let's see what we get. 3 over 9, which is 1 over 3, plus 1 minus 1, plus 2, plus 3 over 2 minus 4. So these two guys cancel. Common denominator again is 6. 2 plus 2 times 6, which is 12. 3 times 3, that's 9. Minus 4. We have, let's see. No, not minus 4. 4 times 6, minus 24. Forgot to multiply it. And then what do we get? 23 minus 24 on the top. And then minus 1 over 6. Okay, so why did I subject you to this tedious computation? Well, remember my previous remark, right? That normally the line integral depends on the path and the endpoints. But see, these two examples suggest that under some conditions, or maybe for certain types of functions, maybe that's not the case. Because we got the same answer. And the only thing we change is the path between the 2 points. So what remains the same is the vector field, the initial point and the terminal point on the curves, but different curves, right, between the initial and the terminal point. And then if you're curious, you could do it with Maple. You can pick any other path. As long as the initial point and the terminal point is the same, you will notice that the integral is the same. So then the main question we're going to address in this class, in this section, what is so special about this vector field that makes that the integral over any path doesn't depend, the integral doesn't actually depend on the path, but actually depends only on the endpoints of the path. So that leads to the so-called fundamental theorem of line integrals, which we'll finally introduce it on the next page, so stay tuned. All right, so the fundamental theorem of line integrals, it's actually another theorem similar to the one in Calculus 1, which states the theorem of a certain type of a derivative in the form of a vector field. So more to the point, let's say you have a curve C given by, we're going to illustrate this, by the way, for a curve in the plane, although the idea is the same for, the theorem is really the same for any, for a curve in the space as well. So let's say R of t is given by x of t, y of t, with a parameter domain for this curve for t between a and b. And remember that the gradient, which is kind of like a derivative of a function, the gradient of a function of x and y is actually the vector of the partial derivative, fx of xy, fy at xy. So the fundamental theorem of line integral simply states that if you take the line integral over the gradient field, so not just any vector field, but the vector field given by a gradient. So remember, a vector field is a function whose components are functions of several variables. So the gradient itself is one such vector field, right? So obviously, like with any vector fields, we can take the line integral over it. So the line integral over this curve of a gradient, so we can write it in the formal notation, gradient of f dot dr. It turns out that the integral depends only of the initial function, whose, that gives you this gradient, f, evaluated at the endpoints on the curve. So the final point minus the initial point on that path. So if you imagine the path here going from position vector r of a to the position vector r of b, remember the initial and the end point, you can illustrate them or denote them either by their position vectors to those points or by the points themselves. It's more compact to refer to it in form of the position vector. So it's the complete analogy to the fundamental theorem of calculus from Calculus 1, except that here you have a generic line or a curve between the 2 points. In Calculus 1, of course, you have a straight segment, and then you have f of b minus f of a. And you can think of f as some sort of an antiderivative of the gradient. There is some sort of terminology, actually. The gradient field, f is also called the, we'll get to that actually with the terminology. Let's not actually get ahead of ourselves. There is a terminology of if a vector field has can be written in form of a gradient, that function that gives that gradient is called the potential, but we'll get to that. So like I said, the theorem simply states that the line integral over the gradient field actually only depends on the endpoints, meaning that you don't actually have to, that's the key thing, right? You don't actually have to evaluate the line integral using the definition and the whole process of actually taking the parametric form of the curve and actually plugging in the curve into the vector field and do all that computation we did prior in the previous page. Let's actually illustrate, so first of all, let's actually prove this. We can actually understand where that comes from, and then we'll see how this connects with the previous example that I started with this class. So this is actually a nice, again, application of the chain rule. going back to the chain rule section, right? So the function f is a function of several variables, 2 or 3 variables, right? So x and y. And in turn, x and y are functions of t. So let's see what happens. Also notice here that if I were to compute df dt, so if I view f as a function of t via this composition of x and y and then x and y with respect to t, via the chain rule, this is nothing but partial f with respect to x at the point xy times dx dt plus partial f partial y at xy dy dt. So this is just the chain rule. And let's see how we evaluate actually the line integral over the gradient using again the typical process we're going to have to do when we evaluate any line integral. So what we do is we plug in the curve into the gradient. So basically this will be the integral over the parameter domain from a to b of the gradient evaluated at the points at the curve x of t, y of t, right? So instead of x and y, you're going to plug in the components of the curve, whatever those are, x of t in terms of t, right? X of t and y of t. And the same thing for the second component, or for the third component if you are in 3D. And then you dot this with the derivative of r of t, which is dx dt, dy dt. You can call, let's dx dt, let's use it like dx dt, dy dt. Or x prime of t, y prime of t. So this is what you integrate with respect to t. Let's do this dot product. So we're going to have partial f with respect to x at x of t, y of t times dx dt plus partial f partial y at x of t, y of t, dy dt. But if we look carefully, in fact, this is just the chain rule that will give me df dt. So as a matter of fact, what you have here in the integral is nothing but, let's see, d dt, the derivative with respect to t of f of x of t, y of t. Again, I hope it's not too confusing. You basically have the whole composition as a function of t. You can view that as a function of t, f of x of t or y of t. But this is nothing but fundamental theorem of calculus from calculus 1. It's the integral of a derivative with respect to t. What do we know from calculus 1? That this is actually the antiderivative, which is just f, evaluated at b, so f of x of b, y of b, minus f of x of a, y of a. But this is nothing but the function that gave you the gradient to begin with, evaluated at the terminal point minus the function evaluated at the initial point. I write it like that to appear in a more compact form, but basically you plug in into the function f the initial and the final point, and then take the difference between the two. So what is the moral of the story related to the previous example? So remember, the previous example showed, involved a vector field. Let's write it again, 3x minus y minus x plus y squared. And the line integral basically was between two curves, starting one between minus 1 and 1 and one and then ending at the point 0, 2. But I can tell you right now, it's not going to be obvious at this point. It will be obvious on the next page after we go through the process. But I can tell you right now that in fact this vector field happens to be the gradient of a function of two variables. Let's take a look at the following function of two variables, namely 3x minus y minus x plus y squared. No, excuse me, that was the vector. So f of xy is 3x squared over 2 minus xy plus y third over 3. Okay, this doesn't come out of nowhere. Just hold your thoughts for a minute on where that comes from. Let's just convince ourselves together that indeed, in fact, my vector field to begin with is in fact the gradient of this function. So what is the gradient of f, of little f? Well, the gradient of little f is partial x, which is 3 over 2 times 2x minus y plus 0. And then partial y, which is 0 minus x plus 1 over 3y squared. So the gradient of this function, little f of x, is 3x minus y minus x plus y squared, which is exactly my original vector field. So I purposely, in the first example, I purposely chose a vector field that happens to be the gradient of another function over a scalar field, right? Over a function of several variables, of 2 variables. So in other words, if you knew this beforehand, if you knew that big F is the gradient of little f given by this function, you didn't have to go through all the troubles to solve the integral directly, right? I mean, with plugging in the curve, taking the parameterization of the curve and so on. You could simply state it that the integral of any curve that connects these 2 points, doesn't matter which curve, as long as they connect the same points, right? So if I take the integral of the second curve, let's say of big F dot dr, because this happens to be actually the gradient of little f, based on the line integral, or based on the fundamental theorem of line integrals, this is nothing but f of 0, 2 minus f of minus 1, 1. I got a little bit greedy here and I don't think I'm going to, well, let me see. I don't want to put the answer here on the second page. Let me see if I can fit it in to convince yourself that this is actually the same answer, minus 1 over 6. So you plug in 0 to for x and y. So if I plug in 0 for x, that's going to be 0 minus 0 plus 2/3 over 3, which is 8 over 3, from which you subtract, let's pay attention here, we have minus 1 for x, so that makes it 3 over 2 minus negative 1 times 1, that makes it plus 1 over 3. Okay, so we have 8 over 3 plus 1 over 3, that makes it 9 over 3, which is 3, minus 1 is 3 minus 1 is 2, and then 2 minus 2/3, excuse me, 2 minus 3 over 2. What did I do here? Give me 1 second. So f of 0, 2 minus f of minus 1, 1. So if I plug in 0, or 0, 2/3, that's 8 over 3, minus negative 1, that's 3 over 2, negative 1 and 1, that's plus 1, and then plus 1 over 3. Oh no, sorry, I made a mistake here, so in my mind, so it's 7 over 3. Let me actually do it in this corner here. So it's 7 over 3 minus 3 halves minus 1. So that makes it 7 times 2, that's 14. 14 minus 9 minus 6. 14 minus 15 minus 1 over 6. So it's going to be minus 1 over 6 for sure. I mean, we know that because that's the theorem. Sorry, I squeezed it in here. So anyway, just take it separately and go slowly and notice that indeed this difference is going to be minus 1 over 6. So as expected. And before we turn the page and do another example, notice that the biggest advantage is that you can take any path. You don't even have to know what the components of the curve are, because as long as the integral is of a gradient, then again the integral depends on the endpoints only. Let me actually illustrate this on the second page so I can see it. We can see it better. So stay tuned for the next page. Okay, so I wrote the theorem one more time, and then again, let's appreciate one more time what we achieved with this. The idea is the following, right? You have various curves, right? So they can be as complicated as it gets, right? And let's say they start at the same point, R of A, R of B, but otherwise there are different curves, right? C1, C2, C3, C4, and so on. If you have to take the line integral over these curves of some vector field, and if you are lucky to notice that in fact this vector field happens to be the gradient of another, shall I say, scalar field, right, a function of several variables, you don't have to worry about the equation of each curve. You don't have to worry about the parametrization of that curve. You only need to know the initial and the terminal point of it, and then the line integral states that the integral is the little f whose gradient is big F at the final point minus f at the initial point. So there is a terminology here. Little f is called the potential of big F if the gradient of little f is big F. It has to do with the analogy with conservation of energy, which we'll talk about in a moment, before we go over how we find this potential, because that's the key thing. How do you find the antiderivative, basically, in the form of this gradient? So little f is called the potential of big F if the gradient of little f is big F, and if a vector field big F can be written as a gradient of f of xy, we say that the vector field big F is conservative. Why is called that way? Because it has this connection with physics, that is to say, with the conservation of energy when you travel between one point to another. So if you are in a vector field, let's say, for example, a force field, the gravitational force field, the force given by the gravity, is an example of a conservative vector field. So the energy spent, or the differential energy spent between one point to another, is the same regardless of the path taken between the 2 points. All right, so then the question is, how do we find the potential? Because obviously it's advantageous. So in fact, two questions we have to address from this point on. So question number one, how can we recognize that a vector field is conservative? That is to say, it has potential. And the second question, how do we find its potential? That is to say, that function, scalar function f of xy, such that big F is the gradient of little f. So we're not going to prove in details the criteria for recognizing that a vector field is conservative, but intuitively, to address question one, suppose, for example, your vector field, generally speaking, has the components, as we have this typical notation, P of xy for the first component, and let's say Q of xy the second component. In most of the literature, this is the typical notation for a vector field. And by the way, this question here we're going to address for now in 2 dimensions, right? So we're going to talk about at this point when we recognizing whether a field is conservative and finding its potential. For now, just for vector fields in the plane, and then we'll switch to how do we address the same thing for 3-dimensional vector fields. So notice that a vector field will have a potential, like I said, if it can be written in form of a gradient. In other words, big P of xy should be the partial x of some function, and then Q should be partial y of another function. Now remember, we know something about mixed derivatives, namely that partial y of x, assuming that the derivative exists and are continuous, is actually equal to partial x of y. So if you look carefully, that is to say, that's another way of saying partial y of the first component, because p is, if it is to be have a gradient field, then p stands for partial x. So if I differentiate p with respect to y, that should be equal to the derivative with respect to x of q, because that's going to be fyx. So as it turns out, for some conditions, for some extra mild conditions, this works in reverse. So you can write this as a theorem, which you're going to provide without proof. If the vector field f is defined There was another little crash on this thing, on the software. Okay, so what I was going to say is that this actually works in reverse, so I have to start the page from the top again. The theorem that gives you the criteria when when a vector field is actually conservative. So it says that if big F, a vector field, is defined on a simply connected domain, this simply means all of the domains we're going to encounter are like that. This simply means that between any 2 points on the domain there is always a path. Excuse me, any path. Yeah, I mean there is always a path that connects them entirely inside the domain. So basically there are no gaps and holes in the domain, not reachable by a path between 2 points. So well, not gaps. So there are no disjoint pieces essentially. That's what it means to be simply connected. So if you have f defined on this domain, then f is conservative provided that dp dy equals dq dx. So it works in reverse under these conditions, right? If the partial y of the first component, let me write it one more time. So partial y of the first component is equal to partial x of the second component. By the way, this is just we're gonna have a similar condition for vector fields in 3D. So this is strictly for vector fields in 2 dimensions. So partial y of the first component equals partial x of the second component. And so now, if you look back at my first example, P is 3x minus y. This is P of xy. And then minus x plus y squared is Q of xy. And so notice that dp dy is equal to minus 1, partial P, partial y. And then partial Q with respect to x is minus 1 again. So they are equal. If they're not equal, then the field is not conservative. Okay, so if dp dy is not equal to dq dx, then not conservative. So let's see how we find the potential once we establish that it is conservative. So this is a neat little technique which involves 2 integrations, a partial integration and another integration at the end. It's very similar. It's nothing special except that one little thing you have to keep in mind when you do the first antiderivative, when time comes to actually add the concept of integration. So you have to be careful with one particular aspect. So let's go slow in the process of how I actually figure out the potential for this vector field, which I gave it to you on the previous at the beginning of this lecture. So you can start with either of the components. So P of xy is 3x minus y, which should stand for partial x of some function, partial x with respect to xy. And Q of xy, which is minus x plus y squared, stands for f of fy, partial y. So basically, the idea is to find f of xy whose partial derivatives are given by these components. You can start with either of the two. It makes no difference in the order of, in terms of difficulty. So you might as well start with the first one. So start with partial x of f equals 3x minus y and integrate both sides with respect to x. So once again, you could do the same approach by starting with the second one, but it doesn't make any difference in terms of the difficulty. Now, just to be clear here we have partial x as a function of xy, which is 3x minus y. But since this is partial x, you can go back to the original by taking the antiderivative of both sides with respect to x. Okay, so the first step is to integrate both sides with respect to x. That gives me the original on the left side, right? So the antiderivative of partial x with respect to x is nothing but f of xy. But pay attention on the right hand side. On the right hand side we have an antiderivative with respect to x. It's a partial antiderivative. So you integrate with respect to x, which we get 3x squared over 2 minus y times x, plus a constant of integration, but this is the difference here, that constant of integration, let's call it k, or c if you want, actually can depend on the other variable. So your constant of integration can still depend on the other variable that you don't integrate yet with respect to. If you want to convince yourself that that's the case, just do a quick partial derivative in reverse here, right? So what is the partial x of the right hand side? So it's going to be 3x, which you need, right? Which is part of partial x, minus y. And then what's the partial derivative of some function of y with respect to x? Well, with respect to x, the partial derivative is 0. So my point is that you cannot assume that that constant of integration is just a number, a real number. Since we have a function of two variables and we have the partial antiderivative, that still can depend on the other variable, which is y. And most of the time it does explicitly depends on y. So we know already the format of the potential. The only missing part is that we don't know yet what is that integration constant, or shall I say, portion that may depend just on y. Constant with respect to x, but may still depend on y. How do we find it? Well, now it's time to actually make sure that this potential fits the second partial derivative. So the partial derivative with respect to y needs to match the second component of the vector field. So now I'm going to take the partial y of the potential function that I just found, including the unknown piece of it, k of y, take partial y of it. So what is partial y? That's going to be 0, because that's with respect to y, minus partial y of minus yx, which is minus x, plus the derivative of k prime of y, right? That's a single variable function, so it's just k prime of y. And this should match the second component of the vector field, minus x plus y squared. If indeed the vector field is conservative, the portion in x should cancel. This is the place where that condition dp dy dq dx actually makes sense here. So unless you did a computation mistake or the vector field turns out to be not conservative, the x should cancel and you should be left with just a simple derivative with respect to y, which you can easily integrate, so you can find k of y. So now if I integrate with respect to y, k of y is y third over 3, plus a constant c, but c now is actually not needed. I mean, I'm going to put it here just for completion, because the potential function is not unique, right? So the potential for the big vector field, big F of xy, is 3x squared over 2 minus xy plus y third over 3 plus a true constant. This time actually this is an actual number, a constant real number, People usually don't actually write it here, because if this is for the purpose of evaluating a line integral, once you plug in the initial and the end point and you take the difference, the constant will cancel, just like in calculus 1. So for all practical purposes, we can pick the potential to be this portion here without plus c. And we use it in the previous page. So we're going to do another example, and then I'm going to have to make a couple of remarks on the meaning of these, some physical interpretation of these vector fields, conservative vector fields, and then we can finally call it a day. And let's hope this thing doesn't crash anymore, because it's soured on me quite a lot on this nice lesson. It's one of the nicest and important lessons, actually, and I had 2 crashes on the software so far. Let's hope we're not going to have a third one. So stay tuned for the next page. Okay, let me introduce you with another notation while we go over the next example. So let's say I want to find the line integral over some curve, which let's say is from, so C is some curve from 1, 0 to 2, 1. I don't specify the curve because this will be a conservative vector field, but just be careful in actual problems, because sometimes they do mention what the curve is. And if you do not check and notice that the vector field is conservative, you're going to spend quite a lot of time doing the integral explicitly by plugging in the curve. And that may result in a lot of tedious computation, or maybe even impossible computation to do by on paper if the curve is really complicated. So here another notation you may see for line integrals of vector fields in the plane is that the components are given in the form of a dot product with dx and dy. So here's the you can have this type of notation: p of xy dx plus q of xy dy. That's another formal notation for a line integral over a vector field with components p and q. So that's like big F of xy is given by p of xy, q of xy. And instead of actually denote this by big F, you can just put it directly in the dot product between this and dx dy, right? Because remember, dx dy is another shortcut or another formal notation for dr, right? The derivative of the curve itself, if you imagine that r is actually given by the components x of t, y of t. So dx dy is like a shortcut for the dr, for the r prime. So let's say in our example I want to compute the line integral of 2x e to the minus e to the minus y dx plus quantity 2y minus x squared e to the minus y dy. So sometimes you can have the integral given in this fashion from the beginning, right? So in that case, be careful to identify immediately which portion stands for the first component of the vector field, p of xy. It's the one that is multiplied by dx. And the second one, which is, in this case, 2y minus x squared e to the minus y. Okay, so let's check to see if the vector field is conservative. We're going to evaluate dp dy. So the partial with respect to y, that's 2x e to the minus y, and then with the chain rule minus 1. So that makes it minus 2x e to the minus y. And then dq dx, 2y disappears, e to the minus y is a constant, so that's just minus 2x e to the minus y. So indeed, the two are equal. So now we're convinced, we convinced ourselves that this is a vector field. So let's proceed in finding its potential, that scalar function f of xy, such that the gradient of it is the vector field itself. So we begin by, like before, we begin by setting the partial x equal to the first component, 2x e to the minus y. And then we're going to integrate with respect to x both sides. So on the left side, we're going to have the potential f of xy. On the right-hand side, e to the minus y is a constant, so that's just the integral of 2x. That makes it x squared e to the minus y. And plus a constant of integration, which, remember, can still depend on the other variable, y in this case. Now let's find y by matching the second partial derivative. So fy should match 2y minus x squared e to the minus y. So now differentiate with respect to y the potential. So I get minus x squared e to the minus y plus k prime of y. That should be equal to 2y minus x squared e to the minus y. Once again, if indeed this is conservative and all my computation is correct, anything that depends on x should cancel. And you're left with k prime of y equals 2y. Integrate one more time with respect to y, so that gives me k of y equals y squared, and let's not add any constant at this point. So then the potential of this vector field is going to be, going back here, is going to be x squared e to the minus y plus y squared. Sometimes with practice you can actually spot what the gradient, what the potential is just by looking at the components. Like for example, now I see 2x e to the minus y, 2y minus x squared e to the minus y. So you might suspect that y squared is part of the equation. And you know, it's a little bit of mental computation. You can deduct, you can derive the other component, but you don't have to guess it. You can go through this algorithm and figure it out. So then the integral in the problem is going to be the potential evaluated at the endpoint 2, 1 minus the potential evaluated at the initial point 1, 0. So just like in calculus 1, just plug in the point. 2, 1 for x and y, so it's 2 squared e to the minus 1 plus 1 minus, plug in 1, 0 now, 1 squared e to the 0 plus 0 squared. So when everything is said and done, that's 4 over e plus 1 minus 1, so just 4 over e. Okay, let's do, we're going to do another small, I'm going to do another comment here. This is a longer lecture, as you can see already. One important remark for the next lesson that comes up after this. And I'm going to ask the question and then pause the video and try to answer the question yourself. What if I have a closed curve? And then I ask the question, and I state the following. I state that f of xy is conservative. And then I ask the question, what is the integral of, you know, right? So this is, let's say this is the curve r of t, right? With, but you know, the only difference is that it's a closed curve. And I ask the question is, what's the integral over this curve? Assuming that big F is conservative. So assuming that there is some potential whose gradient is big F. So pause for a moment and answer the question and see how this relates to the fundamental theorem of line integrals. All right, so assuming you did that, it should be pretty obvious the answer is 0. Once again, so that we don't get confused with the next topic and with other problems, both things are necessary, right? A closed curve and the vector field to be conservative. So why the answer is 0? Well, the answer is 0 is because you can actually pick any point on the curve and think of that as both the initial and the final point. I start at the point, let's say this, you know, when you are at this point, that happens for parameter t equals a. And then I go around the curve, and then I go back to the initial point at a time later, call it t equals b. But the coordinates of the initial and the final points are the same. And because the vector field is conservative, the integral of the vector field is f evaluated at the final point minus f evaluated at the initial point. But because these two points coincide in space, I mean, they have the same coordinate, obviously the answer is 0. So Obviously, if it's not conservative, the answer won't be typically 0. All right, and then it may or may not be 0, but not typically 0. Okay, so there's going to be one last page to discuss just a couple of relations with, some physical meaning of these conditions, like when the vector field is conservative and when it's not. Some physical interpretation of these properties, and then we'll call it a day. Okay, so I like to give this interpretation of what it means to be conservative or not in relation to the condition that checks for it. So, and then I'll show you a simple example to visualize. So let's summarize one more time, right? So f is in 2 dimensions this time. Again, we're going to have an equivalent discussion in 3D later on. So f is conservative provided that the domain is simply connected, and also that this condition is set, right? I mean, it's satisfied. The partial dp dx equals dq dy. And then f is not conservative if these two are not equal. Now, think about geometrically a little bit. So this basically takes the first component and looks at the rate of change with respect to, oops, sorry, I put it all the way backward here. My bad. One more time. Okay, so f conservative is if partial p with respect to y is equal to dq dx. And then f not conservative if the two are, of course, not equal to each other. All right, so think about for a moment, right? So the first condition states that in both cases, I compare the derivative of the first component with the other variable. So the first component which goes with the x-axis, but differentiated with respect to the other variable. And then vice versa, right? The derivative of the second component with respect to the first variable. So if you imagine you're immersed in a vector field, and let's say the vector field represents some force field, some force is acting on an object. Intuitively, in the first case, if you pick any point in this vector field, there is no tendency to rotate or to spin at that point. Whereas if these two are not actually equal to each other, there is going to be a tendency to spin, or a tendency to rotate at a given point where this condition happens, where these two are not equal to each other. And again, we can illustrate this with a very simple example in which we have a vector field simple enough to visualize. So when I say spin or tendency to rotate, again, this is like a pointwise property. You imagine yourself, you're immersed in that force field, or let's say a fluid dynamics field, or a velocity field in a fluid. And then when these quantities are distinct, then you look at the vectors acting near that point, and you will see the differential that has this effect. Like if you basically imagine yourself immersed in that fluid, you should feel that the vector field has a tendency to rotate you at that point. So for that reason, a vector field that is conservative is also called irrotational, because there is no tendency to rotate or to spin around that point. And so let's actually illustrate this, like I said, with a simple example. Suppose, for example, that we have a very regular river, regular in the sense that we can illustrate the current in the river with some very simple vectors. So we're going to illustrate the current in a river with velocity vectors, or for the current, for the fluid that goes through the river. So I'm going to do a little sketch here, and obviously it's going to be completely unrealistic, right? But it serves the purpose. So these are the two sides of the river. I mean, the two sides of the river. And let's say, and by the way, let's say the river is aligned with respect to the x and y-axis like this. And let's use actually a different color for this piece here. So let's do blue, since we talk about water, right? So let's say for a given x, the velocity is exactly the same in magnitude, I mean, and then parallel to the x-axis. But as you increase x, it's also the same but shorter. The same with respect to y, that's what I'm talking about, right? So as you change y, the velocity in magnitude is the same. It's parallel to x. And the only difference is that as I progress down the river, it seems to slow down. Okay, so I think that's enough. Let me do another one. Again, just imagine that the magnitudes of these vectors are all the same when I change y. And then comparatively, let's do another example kind of similar to this. But in this case, I'm going to change the magnitude as I change y, and I keep the vectors the same along the x-axis. So for example, as you're closer to the, so let's say the sides of the river are the same, right? So as you are closer to the lower side here of the river, let's say you have these currents, the velocity vectors, same magnitude as I change x. But as I change y, they become smaller. And then as I increase y, they become even smaller. Okay, you get the point, right? But again, imagine that they are the same in magnitude. Okay, so what about that tendency to spin that I was talking about? Well, imagine, for example, that over here, in the first case, well, first of all, let's say actually a possible representation of this vector field. Again, overly simplified. So what could be the components of such a vector field in the first case? Well, this vector field has 0 y component, right? So the second component is exactly 0. There is no up or down in that vector. So that much should be clear. And the first component only depends on x. I hope you clearly see that. It's decreasing in x and depends only on x. It doesn't depend on y. So let's just come up with a simple function that is decreasing in x. Let's say it's 1 over x. Again, overly simplification, completely not realistic, but it illustrates the purpose, right? So this is a typical, this could be a representation of this, right? So, the first component decreases with x, second component is 0. So this will be P and Q. And please notice that this is going to be a conservative vector field because dp dy is actually equal to dq dx. dp dy is actually 0 because it doesn't depend on y, and dq dx is 0, of course, because there's no depends, there's just a constant. If I drop, let's say, a piece, not a leather, just a piece of wood, right, like a plywood, in the form of a rectangular shape here that floats. This wood will slow down as it moves down the river, but it's not going to rotate. It's going to still be parallel to the y-axis. Okay, so no spin, irrotational. If you pick any point, you will feel that you slow down the river, right? So you're going to feel, for example, if it's a force field, let's say if you feel a pressure from the back stronger than the one that moves you down the river, right? So there is a net pressure, coming from the left side. But there is no tendency to rotate given the way these arrows look like. So again, the analogy with the piece of wood is going to look the same as it moves down the river. What is the connection with the conservation of energy? Well, let's talk about, for example, in terms of the work that this vector field can give you if you move from one side to another on the river, depending on the path. So for example, let's do this with a red color. Let's say you decide to go from point A to point B. You want to swim across the river. And let's say you can do either swimming all the way across. If you do that, basically there is absolutely no work, no energy that basically contributes to the motion, neither for the motion or against the motion, because all the vectors are perpendicular to the path. Okay, so no work given to the motion, or if you want, no energy gain or lost that contributes or goes against the motion from point A to point B. Now, what if you decide to go on a different path? If you swim, let's say you want to swim toward the middle of the river downstream here and then swim back to the point B. Well, up until the middle of the river, you're going to gain some energy because there is a portion or a component of these vectors that actually help the motion here, right, along the path. But whatever energy you gain when you get to the middle of the river, exactly the same amount you're going to lose it as you swim back to point B, because those vectors now are against you. So the components along the motion path are going to be against the direction of motion. So again, the net energy expenditure is zero that you extract or give from the vector field. All right, so let's move on to the second example. Let's do the same analysis. Let's say let's come up with some components in this case. So in this case, once again, the second component is zero, right? Each vector doesn't depend on, the y component is zero. There is no up or down on those vectors. But notice that now the magnitude of the vector, the first component, decreases with y. Okay, so we have to come up with a function decreasing in y. Let's again choose a simple one, 1 over y, for the first component. So that could be p, that could be q. And let's check to see if it's conservative. dp dy, now minus 1 over y squared. And dq dx, again, is 0. And so notice they are different. So of course this is not conservative. And there is a tendency to rotate at a given point. Now imagine again you immerse at any point here. I'm not going to sketch this because it's not easy to sketch. But as you come with, if you pick a point on the vector field, because those vectors are of different magnitudes, swimming or, going around you, notice there is going to be a tendency to rotate, if you want, counterclockwise. If we go with the analogy with the plywood, if I drop the plywood over here to begin with, because the current is stronger toward the bottom of the plywood, I hope it's clearly that, it's clear to see later on that the plywood as it flows downstream is gonna be rotated a little bit like that. What about the energy expenditure, or whether the energy gained or spent in moving from one point to another is the same? Well, obviously it's not going to be the same. Again, let's say you decide to swim from point A to point B. You swim across the river. There's no contribution from the vector field because, again, all the vectors are perpendicular. However, if I change the path, things is different now. There is a net gain in energy here because the larger vectors up until the midpoint in the river contribute to the motion. And when you swim against the current, you encounter weaker and weaker currents. So in fact, it might be probably less effort to actually go, depending on the case, it's going to be a net energy differential is not going to be zero in moving from point A to point B. So obviously the line integral is going to depend on the path. So the line integral does depend on the path in this case. So I think that's enough for today. This justifies, this basically explains the origin of the name irrotational for a conservative field. So conservative field or irrotational field means the same thing. And like I said, these in the two-dimensional vector fields, this is the condition when that happens. So that's it for today. I'll see you next time.